We start a new module, ferrite devices. In this module, we are going to cover basics of microwave propagation in ferrites. Then we will discuss the concept of Faraday rotation, and then we will discuss how this Faraday rotation effect is utilized in designing devices called isolator and circulator. Isolator and circulator, they have non-reciprocal transmission characteristics. Isolator will allow transmission of signal in one direction only, and this type of devices and the circulator, actually it can be a clockwise circulator or a counterclockwise circulator, as we have already mentioned, and it can transmit signal from one port to the next port, other port remaining isolated. So, this type of devices are realized using Faraday rotation effect, and ferrite material is used in the design of such devices. We start our discussion by briefly describing what is a ferrite material. Ferrite is a family of MO Fe2O3. Fe2O3 is ferric oxide. M here is a bivalent metal and O is the oxide again. So, M is a divalent metal which can be manganese, magnesium, iron, zinc, nickel, cadmium, etc. Now, these ferrites are ceramic like material with dielectric constant usually 10 or higher, and having very high specific resistivity and relative permeability of several thousands are very common for this type of material. Now, they are prepared by sintering metallic oxides. The magnetic properties of ferrites arise mainly with the magnetic dipole moment associated with the electron spin. Every electron in an atom has a magnetic dipole moment associated with it. Because of mutual cancellation, the total angular momentum of a full shell is 0. So, if the shell of an atom is fully filled, then these magnetic dipole moments, they cancel out each other. Only partially filled shells contribute to the net dipole moment. Now, for transition elements like manganese, iron, cobalt, nickel, etc., new shells of electrons are formed before inner shells get completely filled. So, we have formation of outer shells even when inner shells are not fully filled, and giving rise to partially filled shells. Electron spins in the incomplete shell combine to produce a large effective dipole moment per atom. Now, when these moments they are randomly oriented, the net dipole moment remains small as they cancel each other's effect. An external magnetic field, however, can cause the dipole moments to align in the same direction to produce a large overall magnetic moment. By treating the spinning electron as a gyroscopic top, a classical picture of magnetization process and the anisotropic nature of magnetic properties can be obtained. Let us now have a look at the permeability of ferrites. The relationship between B and H for a ferrite material can be expressed as B here mu is a tensor permeability, as we will see, H, and the tensor permeability for a ferrite biased by a DC magnetic field H naught along Z naught is given by this matrix mu j kappa 0 minus j kappa mu 0 0 0 mu naught. Now, in ordinary non-magnetic material, the permeability is a scalar constant where B is equal to mu H. Similarly, for many magnetic materials, this relationship holds, but when it comes to ferrite, the permeability becomes a tensor permeability, and from this relation we see that every component, suppose only Hx is present, Hy, Hz are 0, then also we will get Bx, By, Bz. So, each field component actually contributes to the all flux density components. So, this type of behavior comes because of the anisotropy present in ferrite material, and this mu kappa, they are defined as mu is equal to mu naught 1 plus omega naught omega m by omega naught square minus omega square. Kappa is equal to mu naught omega omega m divided by omega naught square minus omega square. Now, let us see these parameters. Omega naught is called the Larmor frequency or precession frequency, and it is given by mu naught gamma H naught. H naught is the bias field that is applied, magnitude of the bias field, and gamma, it is the gyromagnetic ratio, and it is the ratio of the spin magnetic moment to the spin angular moment. Now, an electron spin is associated, as we have told, with a magnetic moment, and it is also associated with a angular momentum which is given by h by 2. Now, this angular momentum and the moment due to spin, they are oppositely directed, and this ratio, gyromagnetic ratio, can be calculated as Q divided by m e. Q is the electronic charge and m e is the effective mass of the electron. When this ferrite material, when a bias field is applied to a ferrite material, what happens? This magnetic dipole moment, they try to align along the applied field, and if the strength of the applied bias field is kept on increasing, a scenario will come when all these dipole moments, they get aligned, and this condition corresponds to a saturation condition of magnetization. So, this is denoted by Ms, and omega m is mu naught gyromagnetic ratio gamma into Ms. Now, in ferrite material, we will have waves propagating, and omega is the frequency of the AC magnetic field component that is present. So, we see that the magnetic field and the flux density in a ferrite medium, they are related by this permeability tensor mu. If we change the bias, for example, if the biasing magnetic field is now placed along x direction, then we will get mu to be equal to mu naught 0 0 0 mu j kappa 0 minus j kappa mu. Similarly, we can apply this biasing field also along y direction, and we get the corresponding permeability tensor as shown. Let us now consider the wave propagation in the direction of bias, and which gives rise to Faraday rotation. Faraday rotation is essentially a rotation of the wave polarization as the wave propagates in the media. So, this effect is utilized in design of devices like isolator. So, let us first consider an infinite ferrite medium with a DC bias field H naught is equal to Z bar into H naught. Now, we can write Maxwell's equation in this ferrite media, where we have included this tensor mu. Remaining equations are the same. Now, we consider the wave, a plane wave propagating along z, and for a plane wave propagation we will have del del x is equal to del del y equal to 0, and also let us assume that the propagating fields can be described by E bar is equal to E naught bar e to the power minus j beta z, H bar is equal to H naught bar e to the power minus j beta z. So, we are only considering the phasors. Now, in this Karloffy expression, we will have del del x del del y 0, and therefore, only del del z will be present, and derivative with respect to z will give minus j beta. So, we can write j beta E y is equal to minus j omega, and then we will have mu h x plus j kappa h y. This will come from this term, and once we write the field components separately, we get these three equations. Similarly, from Karloff H equal to j omega epsilon E, we will get this set of equations. Now, from this set of equations, we observe that the wave admittance H y by E x is equal to omega epsilon by beta. Similarly, minus H x by E y is also omega epsilon by beta. So, we write y equal to H y by E x, which is equal to minus H x by E y is equal to omega epsilon by beta. Now, once we substitute, for example, here we can substitute H x in terms of E y and H y in terms of E x. Similarly, in the second equation also we can substitute H x and H y in terms of E x and E y, and once this is done, we get a set of two equations j omega square epsilon kappa E x plus beta square minus omega square mu epsilon E y equal to 0. Similarly, beta square minus omega square mu epsilon E x minus j omega square epsilon kappa E y equal to 0. Now, we have the set of these two equations, and for this equation to give a non-trivial solution, we must have this determinant formed by the coefficient of E x and E y has to be 0, and therefore, we get omega to the power 4 epsilon square kappa square minus beta square omega square mu epsilon whole square must be equal to 0. So, from this condition, if we solve for beta, we get two possible propagation constants. We denote them by beta plus and beta minus. So, the beta plus will be omega root epsilon mu plus kappa, and beta minus will be omega root epsilon mu minus kappa. So, we see that in the same media now we have two propagation constants, and this beta plus and beta minus will give rise to wave propagation with different velocities. We will see how we can infer Faraday rotation, which corresponds to rotation of polarization of the wave with distance, by considering these beta plus and beta minus. So, we find that when a plane wave it propagates in a biased ferrite media and the bias is applied along the direction of propagation, we get two values of propagation constants which are denoted by beta plus and beta minus. Let us now consider the field corresponding to beta plus. Beta plus is given by omega root epsilon mu plus kappa, and when this substituting beta plus in this equation, we get E y is equal to minus j E x, and therefore, we can now write the electric field corresponding to beta plus as E plus equal to E naught x cap minus j y cap e to the power minus j beta plus z. Now, these are the unit vectors. Now, this electric field, it corresponds to a right hand circular polarized wave or an RSCP wave, and we can get the corresponding magnetic field as H plus equal to E naught y plus j x cap plus y cap e to the power minus j beta plus z. Here y plus is the wave admittance corresponding to beta plus and is given by omega epsilon by beta plus, which can be written as root of epsilon by mu plus kappa. In the same manner, we can find that the fields associated with the propagation constant beta minus are LSCP or left hand circularly polarized, and therefore, we can write E for beta minus E and H expression as shown, and y minus the wave admittance corresponding to beta minus is given by under root epsilon by mu minus kappa. These RSCP and LSCP plane waves are the source free modes in ferrite medium biased in the z direction. These waves have different propagation constants. Now, let us consider a linearly polarized electric field at z is equal to 0. So, at z is equal to 0, the electric field E, which is directed along x, can be written in this form, and therefore, at any z we can write E as E naught by 2 x cap minus j y cap e to the power minus j beta plus z plus E naught by 2 x cap plus j y cap e to the power minus j beta minus z. And this can be rearranged in this manner. E is now actually sum of an RSCP and an LHCP wave, and the electric field expression can be rearranged in this manner. So, when this e to the power j beta plus beta minus by 2 z is combined with this term, we get this expression. So, the total electric field now can be written as E is equal to E naught x cap cos beta plus minus beta minus by 2 z minus y cap sin beta plus minus beta minus by 2 z e to the power minus j beta plus beta minus by 2 z. And this represents a linearly polarized wave whose direction of polarization we will see rotates as the wave propagates along z. Now, the angle phi, which represents the direction of polarization with respect to x axis, is given by tan inverse Ey by Ex, and this will be minus beta plus minus beta minus by 2 z. So, as the wave progresses, the direction of the electric field, it rotates with z, and this type of rotation of polarization with distance, this is called Faraday rotation. Now, this Faraday rotation is an important property of ferrite biased by a magnetic field, and we will see how this property is utilized in designing microwave devices such as isolator and circulator. An isolator is a non-reciprocal transmission device. It is used to isolate one component from reflection of other component in the transmission line. An ideal isolator provides lossless transmission in one direction and completely absorbs the power in the opposite direction. Isolators can be designed in different ways. We will discuss the isolator based on Faraday rotation. A circular waveguide is used in the design, and a cylindrical ferrite is placed along the axis. The ferrite rod is biased and length of the rod is adjusted to provide a phase shift of 45 degree for the electric field. We have seen that Faraday rotation will rotate the polarization of the electric field. So, the length of the rod and the bias is adjusted so that the polarization rotates by 45 degree. Both the input and the output ends of the circular waveguide, it is tapered to rectangular waveguide sections, and the two ports are at 45 degree to each other. So, the structure is shown here. We have a circular waveguide section which is tapered to rectangular waveguide at the two ends, and this port 1 and port 2, they are at 45 degree to each other. We have a magnetized ferrite placed here, and also we have two vanes denoted by 1 and 2. These are placed parallel to the broad walls of the rectangular section. So, this one is parallel to this broad wall, and vane 2 is parallel to the broad wall of port 2, one near the input end and another near the output end. Now, let us try to understand how the device shown actually works as an isolator. This is illustrated with the diagram shown in the figure. At the input port, let us suppose this is the polarization of the wave. Now, when this propagates and enters the circular section of the waveguide through this transition, this TE10 mode will give rise to TE11 mode in the circular waveguide, but its polarization will remain same as before, and here this electric field is perpendicular to this resistive vane. Now, this type of resistive vanes actually absorbs the wave if it is the electric field is parallel to such vanes. So, here this electric field being perpendicular, it passes unattenuated, it enters in the ferrite media where it undergoes 45-degree rotation, and this is shown here. Now, after this 45-degree rotation, this vane 2 is placed with its plane parallel to this edge, and therefore, this field will appear perpendicular to this vane and it will pass unattenuated, and finally, because of the transition present here, the wave will appear in the output port 2 unattenuated. Now, if we consider a wave incident in port 2, which may be because of some mismatch, some reflected signal appears at port 2, this will now undergo a rotation of 45-degree. Please note that bias in this case is opposite to the direction of propagation. So, with respect to the wave propagation, the rotation will be now counterclockwise, and as a result, after passing through this ferrite rod, the electric field component, the reflected field component will become parallel to this resistive vane, and it will get absorbed by this vane and will not appear in port 1. Now, when this field is incident at vane 1, if there is any reflection from here, this will be rotated by 45-degree by this ferrite rod, and it will come in parallel to vane 2 and it will get absorbed. So, let us summarize. The wave incident on the input port excites TE11 mode of circular waveguide with electric field polarization same as that of the incident wave. Electric field of incident wave being perpendicular to the resistive vane 1 is not affected by it. The electric field polarization is rotated by 45° clockwise with respect to the direction of propagation by the ferrite rod biased by a magnetic field in the same direction of propagation. After rotation, the field is perpendicular to vane 2 and therefore not affected. Since the orientation of the output port is 45° with respect to the input port, the wave passes unattenuated to the output port. For any wave incident at port 2 after travelling past the ferrite, the electric field vector rotates counterclockwise by 45°, becomes parallel to resistive vane 1 and gets absorbed. Any reflected wave from vane 1 if present will get absorbed in vane 2. So, this is how this type of Faraday rotation isolator will provide only unidirectional transmission from port 1 to port 2 and not from port 2 to port 1. We have seen the operation of an isolator based on the Faraday rotation in ferrite. Now, let us see how this Faraday rotation effect in ferrite can be used to realize a 4-port circulator. Here we show the schematic of a 4-port circulator. Different sections are shown. So, we have a rectangular port and from this rectangular port we have a transition to a circular waveguide section. Within the circular waveguide we have a ferrite rod which provides 45° rotation and an axial magnetic field biases this ferrite. Next, we have the port 2 which is again a transition from circular to rectangular, but this time at an angle of 45° with respect to the port 1. We have 2 additional rectangular ports which are on the circular waveguides and the positioning of these ports are as shown. So, port 1, with reference to port 1, we can see that port 2 which is 45° placed and the angle between port 3 and 4 are again 45°. So, let us see how this 4-port circulator operates. So, in this 4-port circulator all ports are kept matched and transmission of power takes place in cyclic order. That means 1 to 2, 2 to 3, 3 to 4 like that. Based on the principle of Faraday rotation, a magnetized ferrite rod is used to provide a 45° rotation of the electric field. All 4 ports in the circulator are arranged such that E field is coupled to these ports in numerical order after going through a rotation of 45° in clockwise direction. So, referring to this figure, whenever a signal is incident at port 1, E field vector will in the direction of m. So, this is the E field vector. Now, as the wave travels along the magnetic ferrite, the direction of E field vector gets rotated by 45 degree and it coincides with n, and therefore, the power incident at port 1 will now appear at port 2. The power does not get coupled to port 4, since port 2 and 4 are at 90 degree with respect to each other. Similarly, if power is incident at port 2, it will appear at port 3 after Faraday rotation of 45 degree. This vector will be parallel to the opening of port 3 and it will excite port 3. And what we can do, a 4-port circulator can be converted through a 3-port circulator. We studied already 3-port circulator, basic 3-port circulator while discussing S parameter. So, a 4-port circulator can be converted to a 3-port circulator by terminating one of the ports into a perfect short circuit. Here we show the schematic of a 3-port circulator. When port 1 is input is given at port 1, the power appears at port 2 while port 3 remains isolated. So, we have perfect transmission from 1 to 2, 2 to 3 and from 3 to 1, and we do not have zero transmission in the other direction. Then we will have the S parameters S1 to 2, S2 to 3 and S3 to 1. All this S parameter magnitude will be unity. Now, this type of 3-port circulators can be realized either in the form of strip line junction in the form of a Y junction or in the form of a waveguide circulator. In case of a strip line junction circulator, we have the ground planes on the top and bottom, and between the strip line conductor and the ground plane are the ferrite discs, and a magnetic field is applied along the axis of this disc. Similarly, in case of a waveguide circulator, we have a ferrite post. Once again, an axially magnetized rod or disc is placed at the center of the symmetrical junction of 3 identical waveguide or strip line type transmission lines as shown in the figure. The ferrite rods are magnetized by a static B0 field applied along the axis, which gives such junctions non-reciprocal properties, and suitable tuning elements are placed at each arm to make S11, S22 and S33 equal to 0, so as to obtain the matching. For the strip line case, as we have seen, two ferrite discs fill the space between the center metallic disc and the ground planes of the strip line. The strip line conductors form an junction and at 120-degree interval. Now, in the absence of any bias field, the ferrite discs, they form dielectric resonator and has a single lowest order mode with a cos phi or sin phi type dependence. When the ferrite is magnetically biased, this mode breaks into two resonant modes having slightly different resonant frequencies. The operating frequency of the circulator can then be chosen so that the superposition of the two modes add at one port and cancel at another port. So, in that way, when one port is excited, the power get couples to one port and other port remain isolated. So, this is in brief the operation of 3-port strip line type circulator. So, in this lecture we have mainly discussed the properties of ferrite materials. We have seen how we can have two different propagation constants in a biased ferrite media, and then we have seen how the polarization of the electric field rotates as it propagates in a biased ferrite media, giving rise to what is known as Faraday rotation. And then we have discussed how this Faraday rotation effect can be utilized in realizing an isolator and a 4-port circulator. Apart from 4-port circulator, 3-port circulators based on ferrite are also very popular, and we have discussed the basic construction of such circulators. So, with this discussion we come to the end of this module, and in the next module we will discuss some basics of microwave integrated circuits. We will discuss different types of planar transmission lines that are used in MICs. Then we will discuss some of the discrete components such as inductor, capacitor and resistors. We will see how hybrid and monolithic microwave integrated circuits are realized using this type of planar transmission lines and components.